Started this chapter on magnetism and talked a lot, and you asked a lot of questions too. So this beautiful effect, what is it called? And this was explained as the charged particles from solar flares interacting with the Earth's magnetic field. Okay. Then we saw that every magnet has a north pole and a south pole, and the poles are at the ends of the magnet, but not really at the ends. I don't think we went into detail, so I just want to tell you that if the length of a magnet is given, that would be called the geometric length. The magnetic length would be the distance between the poles, and you can see that the magnetic length is slightly smaller than the geometric length. See that? Slightly smaller. So the poles are not exactly at the ends, is what I'm trying to say. It's just a little bit in. So the concept there is the magnetic length is less than the geometric length. And the most powerful form of a magnet is which one? The horseshoe magnet, and we've discussed that. That's because of its geometric shape, bringing the poles together. Another important point in magnetism is that you cannot isolate poles. You cannot isolate them. You can never have what's called a monopole. Mono means single. You cannot have just a north pole or just a south pole. You got to have them as a dipole. That's the next concept. So monopoles do not exist. No monopoles. Magnetic poles always exist together as north and south. So it's called a dipole. That is the next one. Then we did see that the Earth has a magnetic field of its own. And I told you that the geographic North Pole and the geographic South Pole, what did I say? Does it coincide with the magnetic poles? No. So there, because of your questioning, I had to say that. And to say that there is an angle between the geographic meridian and the magnetic meridian and so on. Told you that. You don't need it, so I'm not going into that. But what you need to know is, when a magnet is freely suspended, it always points in the north-south direction. But don't get me wrong. If the magnet's north pole is this way, what's the pole of the Earth here? Now that's what everybody says, but it's not true. Now this is called the North Pole is because it's called the north-seeking pole. What do you mean by seek? Looking for. So that's an important concept for you to remember. So the North Pole is not against the South Pole. It is called the North Pole because it's looking for the North Pole. Is that making sense? Yeah. And the South Pole is looking for the South Pole. That's how they have named it. I know that usually, unlike poles, do what? Attract, and like poles. But that concept should not be applied here is what I am saying. Then we discussed that certain materials cannot be magnetized while some can be. What's the reason? All materials have magnetic domains, right? The atoms are magnets, tiny magnets. In the unmagnetized state, how are the atoms? In the unmagnetized state, the domains are they all lined up? No, they are in different directions cancelling out. But when you magnetize them, you can see when you try magnetizing them, they start turning and finally they all get aligned in one direction. So, if you can do that to a material, it's called a ferromagnetic material. That's another word that you may need to know. A ferromagnetic material can be magnetized. The best example is iron. You can have cobalt or nickel, These are all ferromagnetic materials. In fact, I just want to go ahead and say there are three types of materials. Ferromagnetic materials are strongly attracted by a magnet. Magnetic materials are repelled by a magnet. Dia means opposite, right? That's why you call it a diameter, joining the opposite points of a circle. So diamagnetic materials are repelled by a magnet. Did you know that some materials could be repelled by a magnet? No. So, and then there are paramagnetic. They are weakly attracted by a magnet. Now, why are we focusing more on concepts? I've told you this many times. More than the formulas. For you, it's the concepts that you're going to use later on. That's why. Paramagnetic materials are weakly attracted, dia repelled, and ferro strongly attracted. So those are the three types of materials. Well, unlike poles attract and like poles repel. We talked about that. If you break a magnet into two, you will get two magnets, right? You continue the process. As long as you keep breaking it, you will always keep getting two different magnets. So you cannot have a single pole. They always exist as two poles. You can see that. If you heat a magnet, it will lose its magnetism. Did we talk about that? You drop a magnet, it will lose its magnetism. Then we also talked about the magnets used in an MRI are superconducting magnets because you need what kind of a magnetic field? Strong or weak? Very strong magnetic field there. And then I saw a hand go up. If you look at the diagrams on the screen, you will see on the right side the magnetic field of a bar magnet. Now, it's called a bar magnet because of its shape. It's a rectangular magnet. And you can see these are iron filings, means iron powder, showing that the lines are closed. Do you see the lines? And although you cannot see the direction here, they go from north to south and continue inside. Now, that's a big difference between an electric field and a magnetic field. What's the difference? A magnetic field does not start on the north and stop at the south. In fact, it continues inside from the south to the north. So a magnetic field is a loop. That makes sense? It's a closed loop. That is not true for an electric field. Now, what's important is what do you see on the left-hand side? It says it's a current-carrying coil. Can you see the turns of the coil? You know what a coil is, right? There are so many turns. And you can see the coil, the upper part of the coil. Of course, it's going down and coming back up again. You could have made that. And when it carries a current, just look at the patterns. What do you say? What do you say? These are iron filings again. There is no magnet here. It's just a coil carrying a current. And what can you see? What can you say about the fields? They're similar. Which shows that a current carrying conductor always produces a magnetic field. It's worth writing down. If you have a current, you have a magnetic field. A current carrying conductor always produces a magnetic field. Go. Now that's an electromagnet. What's an electromagnet? You have a coil around a ferromagnetic material. So if you simply have a coil here, so if I take a pencil or a pen and then wind a coil over this and remove the pencil, what's inside the coil? What material is inside the coil? No. I said you wind it on this pen and remove the pen. And so you only have the coil. What's inside? Air. So that's called an air core coil. The core means what's inside. So, will it produce a magnetic field? Yes. It will produce a tiny magnetic field. But now if you take that same coil and insert a piece of iron into it, like here, the magnetic field suddenly increases. Obviously, because of the presence of the iron. Now you understood that if you substitute the air core with an iron core, the magnetic field is going to increase. You understood that? So, let's say that it increases 10 times. This is just an example. Now, the number 10 is called the relative permeability of iron. Now, we've heard of permittivity, have we? That is related to charge or electric fields. Permeability is related to magnetic fields. Both words mean the same. What do you mean by permeable? Hey, that's a word in biology. Semi-permeable means what? Pass through, isn't it? So, which of these two materials, air or iron, lets a magnetic field pass through it easily? Sure. In fact, if you have a uniform magnetic field, okay, and you bring a piece of iron and keep it here, you know what will happen? These lines will be pulled into it. That makes sense? Which means the magnetic field loves to move through iron because it's easier to move through iron. So iron has a greater permeability than air. I'm focusing on the concepts. Okay, so that is what you see there. Well, I don't know why. Have you even seen a floppy disk? Have you? Yeah, floppy a long time back. Well, at least we have what? Have you seen a cassette tape? Tapes. Huge recording studios still use tapes. But now I want to tell you how the information is recorded on the tapes or on the floppy. It's because on the floppy or the tape there is a magnetic material coated. And then there is a recording head that passes. You see this recording head? It's a magnet that passes touching that tape. What do you have on the tape? I told you, you have a magnetic material, something that can be magnetized on a piece of plastic. Tape is plastic, you know that, right? On top of that, you have magnetic material that gives it the color. So when the magnet brushes or the tape moves, magnetism is induced, as you can see. So each tiny magnet there turns and aligns. You see that? So if you're singing a song, the sound wave is converted into electric current, and the electric current exists only when you are singing. So when you say, there is a current. And so when that passes by, you see those magnets turn. And then there is a silence. What happens? Nothing. So you have a gap. Please to understand the basic. Now the hard disks. We are even getting away with hard disks now. But you know what I'm talking about? The hard disks in a computer? It's magnetic storage. The hard disk in a computer is a magnetic storage. But a compact disk or a DVD is not magnetic storage. Do you know how it's stored there?
Laser.
Okay, what does a laser do? When you write a CD or a DVD, the laser actually burns through that material. It actually burns. You know that all of computer language depends on a 0 and a 1. It's a binary system. So all you need to know is okay, that's the material. Now I'm talking about what? I'm talking about a DVD. So the laser burns a hole there. It's actually called a pit. It actually burns through the material. You have a 1. If it doesn't burn, you have a 0. You know what I'm trying to say? Mm-hmm. That's all. These zeros and ones are then converted using the software into colors or music or whatever you want. Just think about how that will be. Another problem when you talk about CDs is, I've seen so many people do this. Which side of the CD is more important? Which side of the CD or DVD is more important? I don't know what you mean by the bottom. Is it where it's written?
No.
That is the side that's important. Most people think it's the other way. So I've seen people just keep their CDs carefully with the written part, touching the table, and I go, oh, please. You know what that is? That's a reflector. Because these pits that are made there, when you read it, next time when the laser reads it, if it's a pit, the laser beam will go through the pit and get reflected back. If there is no pit, it's not reflected. Can you understand? So if you keep it with the cover side or the reflecting side down and scratch it, that's the end of the DVD or the CD. Because if that gets scratched, instead of it getting reflected back, it'll go right through. That's when it says, haven't you had this problem many times? Computer cannot read the CD. So next time, when you keep a DVD, put it face down with the cover. When I say cover, you know what I'm talking about. Where it's written, that part up. That's why when you label a DVD, you have to be careful. If you use a pen that can scratch it, that's the end of it. It has to be a soft tip. You can wash a DVD. Nothing will happen to it. In fact, you should, because dust will get into those pits there. You can wash it with soap and water. And someone like, what? Nothing will happen to it. But be careful when you wash it. Again, the reflecting side, don't scrape it off. At least in the summer course, you understand. I just told you that if there is a current carrying conductor, there is a magnetic field, isn't it? Now, if the conductor is in the form of a straight one, like if it's a straight conductor, and you hold it in your right hand palm, everybody knows their right hand. If you hold it in the right hand palm with the thumb pointing in the direction of current, then the closed fingers will give you the direction of the magnetic field. So, if the current is flowing up, you hold it in your right hand with the thumb pointing up, then the direction of the closed fingers towards the tips gives you the magnetic field. You see that? But if the current is flowing down, you can see that the magnetic field did change its direction. Your conceptual questions are mostly going to be based on directions in this chapter. So it's important to know this. I hope you understand.
Four fingers function as a quill.
If you look at, see, this is what I explained just now, very clear. Now look at this. Isn't it the same thing? Okay, now be careful. On this side, how is the magnetic field? Use the words out of the plane of the screen or into the plane of the screen. Remember, it's circular, isn't it? Look, it's like that. So when you reach here, that's the screen. How is it? Out. And what about on this side? In. How do you represent that? You represent that by how you see an arrow. If it's out, wouldn't you see the tip of the arrow? So it's a point. If it's in, what would you see? You would see the tail of the arrow. How does the tail of the arrow look? Cross. Is that clear? So on this side, the magnetic field is, come on, in. On this side, the magnetic field is it always going to be like that? No. What if the current is downwards? Opposite. Well, you just got one question answered, if you got that. If a charged particle moves, did I tell you that it will produce its own magnetic field? Yes. A current always produces its own magnetic field. And what is a current? A current is just the movement of charged particles. So, if you have an electron, let's say you have an electron moving this way. Are you watching? Electron moving that way. That means from my left to the right, or from your right to your left. And there is a magnetic field, not the magnetic field created by its movement, but there's already a magnetic field here, And that magnetic field is up towards the ceiling. No, according to that figure, it's towards you. Let's say the magnetic field is towards you. How is the electron moving? From your right to the left. Yes, it's moving perpendicular. Now, just now I told you these two. This one is the magnetic field, and this is the motion of the electron. What's the angle between them? 90 degrees. Can you see that? That's like the x and the y axis. So wouldn't that be a plane? Hey, that would be a plane, isn't it? That would be a plane. So, again, going back, a charged particle, an electron, is moving at right angles to a magnetic field, and you know what will happen? Immediately a force begins to act on the electron. So, the electron wanted to go this way, but no dear, as soon as it enters the magnetic field, a force acts on it. You know how the force is? Perpendicular to the plane. That means the force is upwards. Again, for this, you have to use your right hand. And that's what is shown in the picture there. Look at that picture. Your thumb gives the direction of motion of the electron. Your fingers give the direction of the, magnetic field. And the force acting on the electron is perpendicular to the palm of your hand, which means it will be up. Is that clear enough? All right? Thumb gives you, let's hear it. The thumb gives you the direction of motion of the electron. The fingers give you the direction of motion, direction of the magnetic field. And the force is perpendicular to the palm, means perpendicular to the plane.
That's only on a negative charge.
That's only on a negative charge. If it is a positive charge, then look at what I did. Did you see this? And there is a diagram for that, but I just wanted to first give you the formula, and then we'll look at that. So now we're talking about a negative charge, as far as the direction is concerned. But the force is given by QVB sine theta. All right, what are they? What is Q? Charge of the particle. Then you have the velocity of the particle. Then you have, what's that? B, the strength of the magnetic field. And theta is the angle between the velocity and the magnetic field. In this case, what was theta? 90. For you, most of the time, it will be 90. What is sine 90? 1. Sine 90 is 1. Therefore, Q max, F max, I mean, see, that's why this formula became this. So, force is this formula, but if theta is 90, sine 90 becomes 1. So, maximum force is QVB. So, in the exam, if I ask you, what's the maximum force, don't ask me for the theta. Because if I say maximum force, then you know the theta is 90 degrees. So what's the concept here? The concept is, for maximum force to act on a charged particle, it should move at right angles to the magnetic field. You should have got that. For maximum force to act, the charged particle must move at right angles to the magnetic field. Isn't that what we've been saying? Yeah, so F is QVB sine theta, and then if theta is 90 degrees, force becomes maximum. So that is the formula for maximum force, since sine 90 is 1. What's the use of knowing how much force acts on a charged particle? This is one of the things that's most useful. But to understand the next formula that's coming up, I need more concentration. We're still talking about an electron. Watch this. Some of you may miss this. So an electron starts moving, and let's say there's a lot of area in which the magnetic field is, okay? So as soon as the electron enters, what's going to happen? Wouldn't the force act on it upwards? Mm-hmm. So what will happen to the electron? Can it continue moving straight? What will happen? Wouldn't it turn a little bit? All right. When it turns, wouldn't the force also turn? Because the force has to be at right angles to your palm. Come on now. So first the force was like that. Now, when the force acts on the particle, it's going to get a kick. So it's going to go a little bit. Now, as soon as that happens, what happened to the force? Turn 2. And so it'll turn again. You see that? So it'll turn again. And if the area in which you have the magnetic field is big enough, you are compelling the charged particle to make a circular path. And it'll keep going around in a circular path. When anything moves in a circular path, there is a force acting. Does anybody know what that force is called? I don't think I've written that here. What's the force called? Centripetal force is given by the formula. Just imagine I forgot. That will be the end of the class, right? What's the formula for centripetal force? That's from college physics 1. How do you expect us to remember that? Okay, fine. Do you at least remember? Now, what are the terms? M, mass of the particle, so it will be the mass of the electron. R would be the radius of the circular path, and this would be the velocity. So, this must be equal to QVB. Wait, this is the general formula for centripetal force, isn't it? Now, in this case, we know this is the force, don't we? Put them both together, cancel out one of the velocities, because it's a square, and then make radius the subject. What do you get? What's the formula?
QB divided by...
Is it or the other way around?
MB.
MB divided by QB. So that's a formula that you have to know. It's on your formula sheet. What does that formula tell you? This formula tells you that bigger the charge, smaller the radius. Come on. That's true. Because if the charge is bigger, bigger force acts on it, so it's going small radius. Bigger the mass, bigger the radius. Well, if the mass is big, you cannot deflect it so quickly, so it'll go, you know what? Try to think, if it's a heavy particle, it's not going to easily turn, is it? Like, if you're driving an 18-wheeler, you would know what I'm talking about. You can't turn like you're turning a tiny car. Mass is so heavy. So think in those terms to be able to answer conceptual questions. What if it's moving with high speed? Would the radius be bigger or smaller? Bigger. Makes sense again. It's moving so fast. So by the time the magnetic field acts on it, it'll have gone further away, so the radius would be bigger. What about the strength of the magnetic field? If it's higher, then the radius will be smaller. All right? I've answered 4 concept questions for you right there. Expect 1 on the exam. So far, we were talking about an electron, correct? Now, the situation has changed. Now we're talking about, watch, a positively charged particle. It's the same rule. A positively charged particle, it says west in this case. Is that the west for you? Yes, it is. And then the magnetic field is towards the north. The force would be, again, perpendicular to the palm, which in this case would be down. Make sense? Come on. That's it. So you should be able to answer both. Now, I do want you to pay attention to what the charge of the particle is. Don't just be crazy, like say, half asleep, you just say, all right, he said perpendicular to the palm. Yeah, that's true. But you have to make out if it's up or down by using this. Well, what I told you just now, I'll spend 10 seconds on this. It's called a bubble chamber, and you cannot see these tiny particles, can you? Electrons and all that, but you can. Have you seen a jet pass by and you see the trail that it leaves behind? In the same way, in a bubble chamber, you cannot see the electrons, but you can see the trail that they leave behind. How cool. Tiny bubbles. And if you measure the radius of that circular path, knowing the other quantities, you can calculate the charge of the particle. That's how the charges of many fundamental particles have been calculated. Because when I throw numbers like the charge of the electron is 1.6 times 10 to the negative 19, it did not drop out of the sky. Somebody had to find it, correct? So that's called a bubble chamber, cloud chamber, bubble chamber. There are many types, but that's all I will say. Now look at this diagram, and that's the formula that we were talking about. Did we talk about that formula? Someone like, did we? I think so. All right. Because you have the diagram, what do these crosses, X's mean? What is going in? Magnetic field is perpendicular to the plane in, isn't it? How is the particle moving? As you can see, the green arrows. Isn't it moving? And it says it's a negatively charged particle. Did you notice? If it's a negatively charged particle, is that correct? The direction of the force is into the center. Is that correct? Check it out with your hand. How is the magnetic field? Which one shows the magnetic field? No, you don't know. The fingers. So how's the magnetic field? Into. Isn't it? And how is this moving? How would you hold your hand now? Like that? I don't know. If you hold your hand like that, the magnetic field is like this. But I think the magnetic field is into the plane. So you have to hold it this way. And then the electron is moving. How is it moving? I can't, with my hand, I can't show you with that. It's moving like this, isn't it? That's why the force is up perpendicular to it and it forms a circular path. Okay, we talked about that. Just one thing. Can you disturb a television screen or a computer screen using a magnet? Yes, you can. And obviously, now you know what happens. Because when you bring a magnetic field, the charged particles are upset. See, that is proof that a charged particle has a force acting on it when it passes through a magnetic field. But this is cool. Have you ever heard of an electron microscope? Not in your field especially? And it did not even mention an electron microscope, and then they made a mistake on this. It's called a magnetic lens. Wait, have you heard about a microscope? Yes. Normal microscope? What does it do? Rachel is shaking her head. No. Yeah, I know what that means. What does a normal microscope use? Light bulb. Yeah, light bulb, so light. Okay, the microscope does not work if there is no light. Like in a dark room, however powerful the microscope is, you cannot see anything. So it's light that is focused by lenses. But that has a magnification of like 500 or 1,000. You know, you can change that. But an electron microscope has a magnification of like 100,000. You heard about it. That's where you're able to see the viruses, not using these small microscopes. So, in an electron microscope, it's not light that is being used. It's a beam of electrons. And what is going to focus the beam of electrons? A magnetic field. Just now, didn't we study that charged particles are affected by a magnetic field? That's the diagram shown. You see that a charged particle moving through a magnetic field can get aligned. You see that it's becoming narrower and narrower. That's what you mean by focus. So it acts like a magnetic lens, not a magnetic mirror. Generally, it may be right, but I don't like that. It's a magnetic field. So, can I ask you how an electron microscope works? I mean, the concept. You should be able to say it's because a magnetic field focuses a beam of electrons. That's it. That's why you're having to do college physics too. Because the idea is that you have to know whatever you're using. So if you're using an electron microscope, at least you should know the fundamental of how it works. That's why you're having to do this. In the diagram, you see a current-carrying conductor. So actually, you see a circuit. You see the battery there? So current always flows from positive to negative. Hold on now. What direction are the electrons moving? Negative. Okay. So you have to keep that in mind. And so if this current carrying conductor is kept in a magnetic field, as you can see, what's the direction of the magnetic field? Direction of the magnetic field. North to south, always. So in this diagram, the magnetic field is towards your right. You see that here? And the current is flowing this way. But we know that the electrons are flowing opposite. The force acting on the conductor is given by the perpendicular drawn to the palm of your hand again. So what's the direction of the force? As you can see, it's upwards, isn't it? So any current carrying conductor kept in a magnetic field will have a force acting on it. That's the concept. Any current carrying conductor. You write each time I say that's the concept? Okay. A current carrying conductor kept in a magnetic field will have a force acting on it. And that force is given by the formula I L B sine, I don't know what your text is using, maybe theta or phi. I know. Okay, theta. ILB sine theta. Oh, that's what I wrote. Yeah, it's theta. So this is the force acting on the current carrying conductor. So tell me what the terms are. I of the conductor. Now that's a problem. That is a problem for many. But we'll get to that. What's B? Strength of the magnetic field. What's theta? The angle between the current and the magnetic field. The current and the magnetic field. Now, go back to this and tell me what's the length. In this diagram, what would you take as the length? Would you take the length of this whole part? Or would you only take the length of the part that's between the poles? Between the poles. So if I give you the diameter of the poles, that would be the length. I thought some of you did listen to me. You can have a big conductor. What's the use if you have a tiny magnetic pole? The force will only act where it passes through the magnetic field, isn't it? Okay, so don't be cheated on that. Yes. I'm thinking about a circular pole because I'm looking at this diagram. But just know that the length of the conductor would not actually be its length, would be the length that is between the poles. Is that understandable? Between the poles. Whatever is so if you have big poles, more force. That's what it means. Now this is the principle of a galvanometer. This is the principle of a galvanometer. Have you heard of a galvanometer? No? We're getting there. We are just getting there. I saw your hand up. Joshua, what's the direction? From the north to the south, so it's towards your right, isn't it? Mm-hmm. And you have a rectangular coil suspended there. That's like a loop, a rectangular loop. It's suspended, that means it's capable of rotation. It's like a fiber holding a loop. Wouldn't the force act on 1, 2, 3, 4? Actually, it's 4 lengths. See that? Mm-hmm. But no is the answer. Forces would not act. Let me number them. 1, 2, 3, 4. Somebody tell me on which 2 parts a force will not act. I hope they have not written it. No, they have not. Thank you. Which are the 2 parts? 1, 2, 3, 4. Which are the parts where a force will not act? Well, it's a current carrying conductor. Currents are flowing. Look at that. Which are the parts that are parallel to the magnetic field? 1 and 3. Thank you. 1 and 3. Magnetic field. 1, 3. Either the current is going in the direction of the magnetic field or opposite. So these 2 are parallel. Therefore, theta is 0, sine 0 is 0. No force acts on these 2. But what about these? They are at 90 degrees. Maximum force acts. But here is a problem. Here the current is going down, while on this the current is going up. Therefore, the forces will be acting in opposite directions. So you will have, on one side, you will have a force acting, let's say, towards you, and on the other side, the force would be away from you. I'm not going by the diagram, but you see that. Now, what happens? If two equal and opposite forces act on an object, it creates a rotating effect. You see that? That is called a torque. Have you heard of a torque? How do you calculate a torque? It is one of the forces multiplied by the distance. Yeah, the radius. Okay, the radius. Well, when you say the radius, it will be this, isn't it? Come on, because if you have to look at the circular path, that's the whole circle, so that's the radius. Wouldn't that be half the width of the coil? Is the width of the... Come on. So you get the simple formula. I still don't see it there. I've written it. You get the formula. Half of the width, ILB sine theta. Cos. Oh, when you see this, don't go crazy. What's that? Yeah, tau. That's a tau in Greek. Stands for torque. So that's equal to G ILB sine. Yeah.
Okay, so like if they have equal and opposite like directions, why wouldn't they just cancel out?
I've heard this a million times. So I will demonstrate like I usually do. I've heard this so many times. All right, I'm going to apply equal and opposite forces on these two. Will they cancel out?
No.
Because they acted on two different objects, right? Okay. Now I'll apply equal and opposite forces on this. Will it cancel out? Yes. Now look at a coil. These are the two lengths of the coil. The width is up. One force is acting on this side. The other force is acting on this side. How can it cancel? Well, in this case, it cannot move because it's fixed there, but it can rotate. Good question. Great answer. I'm just joking. I have to look for ways to make you smile. Is that clear enough? Two equal and opposite forces will not always cancel. That was the last part. Now we have to do problems in the remaining time. Yeah, that's all about angular momentum. Oh, that's a galvanometer there. Showing how it works. It's just a coil, see? It's just a coil with a pointer on top. Current pass through that, there's a torque, and you see the pointer move. All instruments work using that idea. This is just a review of